In this lesson, you're going to learn how to calculate the measures of central tendency and the measures of variability. Notice there that I have in parentheses conceptually. A few lessons down the road, we'll be learning how to do one particular measure of variability from a computational perspective. I do want to remind you of a couple of things before we get started. One of them has to do with samples and populations, because remember, we typically do not have access to entire populations, so we have to use samples. The downside of that is sampling error, meaning that quite often our sample statistic does not exactly match our population parameter, but through good sampling and good research design, we can reduce that sampling error to as small as possible, because we want our sample statistics, to be as accurate as possible estimates of our population parameters. Now, when we talk about sets of data, particularly sets of data that are measured on the interval or ratio scale, they are typically summarized by identifying measures of central tendency and measures of variability. Central tendency is what is typical in the data set. So most typicals are in the center of the data set. So we'll be examining that. Think about the picture of Pikes Peak. Variability defines how spread out are the scores relative to one another. So the first measure of central tendency we're going to calculate is the mean. The mean is the arithmetic average. It is calculated by simply adding all of the scores in the data set. So here is the column with all of our scores in it. So we sum those up. That sums up to 57. And then the mean is found by dividing the sum of x divided by n. N for this set of data was 9. So 57 divided by 9 yields a mean of 6.33. Take a few seconds to talk about rounding. What I want you to do for our rounding is to go out to the third digit. If it is 0 to 4, leave the second digit alone. If the third digit is 5 to 9, then go back and raise the second digit by 1. So this calculation was, I believe, 6.33333333, so we're going to round that to simply 6.33. A couple other definitions of the mean. It's one score to represent all scores. Again, arithmetic average, sum of the scores divided by the number of scores. Nextly, let's talk about the median. The median is the middle score in an ordered distribution of scores. So we have to change the order of the scores from highest to lowest. So we created a new column of data here. Because by definition, again, the median is the middle score in that ordered distribution of scores. So there should be an equal number of scores above and below the median. Again, another symbol for that is Q2 or P50, because the median is the 50th percentile. So if you start at the top, count down, the middle score in that distribution of ordered scores is 7. So we've identified it with Q2. And while we're there, we're going to go ahead and calculate our 25th and our 75th percentile. So you'll notice below this 7, there are 4 scores. So we need to divide those scores in half. And what we're going to do is find the middle 2 scores there, which are the 5 and the 4. Add them together, divide by 2. So 5 plus 4 divided by 2 is 4.5. So Q1, or the 25th percentile, is 4.5. And we'll do the same thing in the top 4. So 8 plus 7 divided by 2 gives us 7.5. Next, let's look at the mode. The mode, by definition, is the most frequently occurring score. It is the highest point on a frequency curve or polygon. So here, very quickly, with the small data set we have, we can count and see that there are 3 7s. So the mode of this data set is 7. I want to make a little comment about the normal distribution, or the normal curve. A normal curve is a frequency curve or frequency polygon in which the mean, median, and mode are equal to one another and in the center of the distribution. So again, we've seen that in our picture is worth 1,000-word PowerPoint. Let's move on to our measures of central tendency. We're going to start actually with the kind of least informative, if you will, which is the range. The range is simply the difference between the highest and lowest score. So the highest score here is 9, the lowest score is 4. So 9 minus 4 is 5, yields a range of 5. Next, let's calculate the interquartile range. We've already identified Q3 and Q1. So the difference in those is our interquartile range. So 7.5 minus 4.5 gives us an interquartile range of 3. And remember, the interquartile range marks the middle 50% of the scores. So one way that you can think about that is the middle 50% of the scores are within 3 units of one another. Also think about the box and the box plot. That box represents the interquartile range for a set of data. You'll notice there is a second sheet with this PDF that you're looking at, because I've provided that document to demonstrate how to compute P25, P50, and P75 for various sample size. So we won't go over that in this audio and video, but you might want to take a look at that. And then lastly, let's look at the standard deviation. Again, SD or S indicates how interval or ratio variables are spread across a distribution in relation to the mean. So that's a kind of a little definition for you if you want it. To do that, we're going to calculate 4 separate items: the deviation, variation, variance, and then standard deviation. So let's get started. Deviation is how different each score is from the mean. So the deviation score for 9 was simply 9 minus 6.33, which yielded the 2.67. And then each of those scores in that column are the respective deviation scores for the raw scores. Notice that there are some positive scores and some negative scores, and it's important at this point that we keep the positive ones positive, and we do identify those that are negative or below the mean. One characteristic of this column of data is that the sum of the deviation scores will equal 0 or approximately 0, depending on our rounding. So here it's not exactly 0, but it's 0.03, so that's pretty close to 0, and that does have to do with our rounding. Because we can see that this clear now, but another definition of the mean is that it is the point of the distribution where all of the deviation scores sum to 0. So if you count up the deviation scores above the mean, they should be equal to the deviation scores below the mean. So if we added up all those positive numbers, all the negative numbers, they should be pretty close to each other, so that when we do add them together, it equals 0. The problem with this column of data, though, is that if we want to make other comparisons between groups or do other mathematical computations, the fact that the sum of the deviation scores equals 0 means that makes those comparisons very difficult. So we have to do something to get rid of the negative scores. And so mathematically, what we're going to do to get rid of the negative scores is to simply square each of the deviation scores. So to get rid of the fact that the sum of x minus x bar equals 0, each deviation score is squared. By squaring each deviation score, we eliminate the effect of the negative scores. By definition, again, when we see a column of data, we like to sum it up. So variation is the sum of the squared deviations from the mean, also known as SS, sums of squares. So for this set of data, after we found each deviation score, we squared it. Notice the variation column, there are no negative scores. And then when we sum all of that up, the variation for this data is 24.01. The next thing we need to calculate is something called variance. Variance is the average squared deviation from the mean. Most columns of data in statistics, we add up, and then if we're going to try to find the average of something, we actually divide by n. But if you look up at the top there, or at the bottom in the formula for beside variance, notice that we do not divide by n, but by n minus 1. We use n minus 1, not n, because when we use n minus 1, that results in a better estimate of the parameter of the population. And remember, as good researchers, we want to try to do that as best we can. So we're going to divide by n minus 1. So for this set of data, our variation was 24.01. We divide that by n minus 1, which is 8. So 24.01 divided by 8 resulted in a variance of 3. Variance is also known as the mean of the squared deviations, or the average squared deviation, or simply as mean square. So that's where that MS comes from, mean square, the average of the squared deviations from the mean. Again, there's a little problem with MS, or variance, because notice that we are still in squared units. So the last thing that we have to do to actually calculate our new friend, standard deviation, is to take the square root of the variance, because taking the square root of the variance gets us back into raw score units. So again, standard deviation, we need to get back into raw score units, so we take the square root of the variance, because we're interested not in score squared, but then whatever the raw score unit that we're using. So for this set of data, standard deviation was equal to the square root of 3. And for this set of data, that resulted in a standard deviation of 1.73. So again, this is called the conceptual method. The undergraduate students call it the quote-unquote long method. But I think it's important that we do this because it shows you how every score in the distribution plays a role in what is the standard deviation. Let's finish up this lesson today with another Aggie joke. How can you tell an Aggie airliner when it's snowing? They're the ones with the chains on the propellers. Made me smile anyway.